So I'll start by giving a slide which probably is older than George, but never mind. What's happened to my pointer? Oh, here it is, yes. Now I just wanted to stress that twistor theory, at least to me, is meant to be a theory of physics. So it's done lots of nice things in mathematics too, but the idea behind twistor theory is it's a theory of physics. And one of the ideas is to have a different way of looking at physics, and here we see the sort of basic picture of light rays. Now, one of the main driving ideas behind twistor theory is the Riemann sphere. And here we see one role of the Riemann sphere as the celestial sphere. It's a conformal sphere, and therefore natural to think of as the Riemann sphere. More directly, it's to do with quantum mechanics, where you have superpositions of two states, and if they're states of spin, then you can see it directly as sphere, which is geometrically related to the directions in space. And you see here two aspects of twistor theory. One is to do with relativity, and the other is to do with quantum mechanics. And we find that twistor theory, in some ways, usually one thinks about a theory and it's classical, and then you come to a point where you say, well, you've got to quantize it. Twistor theory is not like that at all. The quantum and the classical things are all mixed up right from the start. And you will see this coming in particularly later on. So I want to talk about that later. For the moment, let me say something else about the Riemann sphere, which was very motivational. And this is that when one has a function on the real line, and you want to divide it, separate it into its positive and negative frequency parts, and this is something important for quantum field theory, the positive and negative energy, and you want to look at the positive frequency parts. I learnt this from Engelbert Schucking, particularly how important that was. It wasn't stressed by other people particularly, but the way I like to think of it was here you have a function, think of the real axis, the axis as this circle, which is the equatorial line here, and that's the real numbers, including infinity. And if you want to know that's positive or negative frequency, the question is, can you extend it? I think positive is actually into the, well, it depends which way around you go here, a circle, so it doesn't matter. Let's make positive going into the top half of the sphere and negative into the bottom half. And this was a great big motivational idea that somehow the things you directly see, the real part here, and there's a sort of hidden imaginary part, and you've got the two sides to it. And twistor theory, one of the big motivational ideas with it has this aspect to it. You have the real things that you see directly, correspond to the light rays, and you have these two sides to it. This comes back much more seriously later on. These things are all very familiar to people, so I won't spend time on it. This is how you describe twistors, omegas and pi's. Some people use other notations here. For me, the omega, well, the pi was the pi because it's really p, which is a momentum. And so pi was a momentum, and omega has to do with angular momentum. And the connection between the two is written down here with these formulae that I'm sure people are familiar with. Notice that the angular momentum depends on both, if you like, the principal null directions of the skew object, which is the angular momentum tensor, are omega and pi. And here you see what happens when you move your origin. So you can think of twistors as a field, that is to say, well, the pi is constant, but the omega varies as you go from place to place because it depends on origin. So you move your origin around and you see what your omega does there. So the question is, what does it look like? And here I have a picture of what it looks like. So here I've got the pi's and the omegas, you can see. As you move around, you might wonder where those things point. You see the pi is constant, that's the momentum, but the omega depends on, if the origin is here, then the omega is there, et cetera, et cetera. Where do these omegas point? Well, you might perhaps not be so familiar with where they point. This is exactly where they point. This picture, which the name Twistor originated from, which is this projected Clifford parallels, And I was familiar with this configuration, and I realized that the Ivor Robinson's notion of how to move a null line into the complex basically led you to this picture. And much later, I realized that this is exactly where the omegas point. So at each point, you see the tangent line to the circle through that point points in the direction of omega. So this may not be so familiar to people, but this is at least a way where you can see this twistor configuration directly as physics. So I wanted to stress again, this is physics, because if you have a if you have a zero rest mass particle with spin, then the omegas describe the angular momentum. The omegas and pi's together give you the angular momentum, and how that depends on position is exactly given by this configuration. So I thought that was worth saying, since the idea of twistors the notion of, or at least the name I should say, also comes from that configuration. Okay, well now I mentioned about quantum mechanics, and here we have what you might call first quantization rules. You see twistors have their complex conjugates. Twistor has an upstairs index, and the complex conjugate is a dual object. And here we have the commutation rules, which are sort of a natural thing to do. They tie in with the angular momentum and all that stuff. That's exactly corresponds to it. And I just wanted to show you, here you have the helicity as being this symmetrical combination of Z and Z bar. And if you put these commutation rules into these formulae for the momentum and the angular momentum, you get the exact commutation rules that momentum and angular momentum have. Now, since this is George Day, I thought I would say something which, George did many things in relation to twistor theory. He certainly had a huge impact on the development of the subject. I know we often had these Friday meetings, and George wouldn't turn up for a while. He'd come in late quite often. And every time he came in, there would be some new idea which would start off conversation in interesting ways. One of the things that he particularly did, let me mention this idea. You see, we had the angular momentum and momentum for a single massless particle. How do you describe massive particles? Well, the idea is that you consider building your momentum up by lots of null momentums, and you can build up the angular momentum at the same time. And then there's a question of what the group is when you consider that this full, now time-like, you add these things up so that the thing remains time-like, that the freedom in how you represent this total momentum and angular momentum with different values of the momenta gives you a group, which is the n-twistor group. And George did more than anybody else to explore how these things work, and I won't go into that here, but I just thought I'd show you this picture because it relates particularly to work that George did. Now, I hope I'm not getting myself confused with my... No, here we go. Now, twistor theory. These are just the twistors again. The zero rest mass field equations are related very fundamentally to twistor theory. Here we have them written in two-spinner form, and you can have the left and right parts of this. I can't quite see which are which, but it says here. So I'm afraid you'll have to forgive me because I can't read my own writing when I'm looking at it because of my bad eyesight, but I hope you can see it. So there we have now these formulae, as Mike Eastwood pointed out, at least certain special cases of these formulae were known to Bateman, and earlier who was it? Anyway, somebody else before Bateman. Sorry? Whittaker, that was the one, that's right. The scalar version was known to Whittaker. Bateman knew one of the versions of the Maxwell equations. And here we have the two versions, one with the pi's. This was the version I had initially with, well, it wasn't written this way initially, but this is basically the initial version I had. And then Lane Houston came along with this version, where you see, if you realize that the Twistor quantization rule, you if you take the complex conjugates, replace them by the derivatives. And so this would get you from here to here. I'm not sure that was the way Lane thought of it, but when he first produced it, I said, well, why do we need this? We've already got this formula. But then I realized the importance of having both formulae. They give you the two different helicities for the different homogeneity degrees. And so that was a very important addition to what we had previously. And that was Lane introduced this idea here. These things basically are understood when we consider that it's really to do with cohomology, and these have to do with, I won't go into why that's true here, because I want to say things which are new here, not things which are old, but I thought it's best to introduce the ideas that you consider actually these things, the Twistor functions can be thought of as overlaps between different patches. Usually you just think of two patches, and then the contour integral goes on in the region of intersection, but the Twistor functions, in general, you would have a whole load of them on a covering of your space with lots and lots of open sets, and then on each pair of open sets you would have a Twistor function on the overlaps, and they all piece together to make sense, and you can understand as a sort of check cohomology thing. Anyway, so these represent all the different zero rest mass fields. Well, if it's spin 0, then you just have the wave equation. And if you have higher spin, then you have the negative and positive helicities given by I think the positive helicity is one with the primes, and negative with the one with unprimes, with the conventions that we use here, if I've got it right way around. And we now have these, again, these are the formulae, and these just give you the different homogeneities. You have a formula minus 2s minus 2 or something, giving you the homogeneity, where s is the helicity, which can be an integer or half integer, so 2s is an integer, and so these numbers are integers, and you see the homogeneity degrees having this curious relationship to the helicities. So let me see, these are the helicities, and that's the homogeneity degree here. This is twice the helicity. That's the homogeneity degree. Okay, well, this is just a linear theory. Let me show you the nonlinear theory. If we, via various ideas that's due to Ted Newman and all that sort of thing, I won't go into the history of it, it became clear that you could actually describe the nonlinear. See, when I talk about spin 2, then this equation with 4 indices is the one that's of relevance, and these are the 4-index spinor, give you the spinor version of the self-dual and anti-self-dual parts of the Weyl curvature. And so the Weyl curvature in vacuums gives you these two equations here. And that was a nice way of bringing all these things together. But it's not playing a role as curvature. This is just linear theory. But what's emerged, as I say, from ideas due to Ted Newman and others, eventually one came across the following. This is the nonlinear graviton construction. Here we have a picture of the Twistor space, and we have lines. This is the flat case here, lines representing points in space-time, and the condition that the 2 points are null separated is the condition that the corresponding lines intersect. Now this is the standard flat space construction, but if you want to do the more general case, we make this what we call a nonlinear graviton. I mean, you can think of this as a graviton wave function. I didn't stress this with what I said. Perhaps I should have stressed it. Let me come back to this picture which I had before. It was a long story before we realized how this really is. You see, here we have the Riemann sphere, and positive and negative frequency can be thought of as your real function is on the axis here, and the positive and negative frequencies go one way or the other. You continue it into the northern or southern hemisphere. And one of the great motivations behind Twistor theory was to have something similar to this, but which applied to the whole of space-time all at once. That was really an idea. And here one sees it in twistor theory, where you have the right-handed and left-handed ones going one way or the other. And it took a long time to realize why this really is this picture here, generalized to, instead of one complex dimension, to 3 complex dimensions. And here you have the Pn being representing the light rays, including those at infinity. And we have the extension into the top half or the bottom half. It took a long, long time to see how this really does represent the splitting into positive and negative frequencies. And to understand that, one had to appreciate first the cohomology. One could see that with contours with funny kinds of shapes, with camel humps poking into one side or the other, would give you the positive or negative frequencies, but it didn't look quite so clean as this picture here. And then it became clear when cohomology became the right way to look at twistor theory. These twistor functions really represent elements of first cohomology, and the first cohomology then splits so that it goes one way or the other, and thus does indeed exactly reflect what one was trying to do here for a long time. I think it took about 10 years or so to realize that this was actually what was going on. So it was rather gratifying to see that that motivation is, once one goes to cohomology, is exactly reflected in this splitting of the projective one-dimensional space, complex space, into projective three-dimensional complex space. But in each case, you have this space in the middle representing what you directly see, and the sort of mysterious quantum aspect to it being the complex thing, which this is a real indication of, and the complex is sort of telling you, governing what's going on, which I rather like the idea of that. That was the idea of twistor theory. Now, let me just see what I'm doing here. Yes. Now you see, everything I've said pretty well here has to do with conformally invariant physics. One's looking at massless fields, and they're conformally invariant, and the conformal structure is what's directly represented in this picture, which I just showed you a minute ago, where you see the intersection between lines in the twistor space, projective twistor space, correspond to null separation. And that's just telling you what the conformal structure is. If you know what where the light cones are, you know what the Lorentzian conformal structure is. But if you want the metric, you need something more than that. So how do you get the metric? Well, there's this object called the infinity twistor, which gives you the metric. And I've written it here. Let's see which way I've written it. That's right. This is not the infinity twistor that we originally had, because originally I was interested in either flat space-time or if we were talking about Einstein's equations, these were Einstein's equations. Yes, I haven't actually fully explained what's going on here. Let me explain the nonlinear idea. The nonlinear idea is that you think of your twistor space is divided. Well, let's think of a neighborhood of a line, because that's really the cleanest. So we're not going to try the thing globally. We imagine close to a line, in other words, in space-time, close to a point. So the neighborhood of a point in the twistor picture would be the neighborhood of a line. And what I'm going to try and do is deform that, and what you can do is split it into two, and then you shift one in relation to the other. And the question is, where are your lines now? Well, they've got ruined because they're broken in the middle. But what you need is a theorem, and this is a theorem due to Kodara, which tells you that if this deformation is not too huge, it's finite, but not beyond a certain limit, then you can still find lines which are analogs of the ones you started with, and they still form a 4-parameter family. That's a Kodara-Spencer theorem, and the Kodara theorem tells you that these still exist. And so these lines form a 4-parameter family, and therefore the points representing these lines is a 4-dimensional space, and you can see what null separation means because its incidence is just the same way here. And what you get here is the general anti-self dual conformal space. If you want a metric, well, the original idea was to see a projection which comes down here. But you can also do this when there's a cosmological constant, and this was worked out in detail by Richard Ward. And then you have to have the infinity twistor, which has a cosmological constant in it. For a long time, I didn't like the idea of the cosmological constant, mainly, I suppose, because I was trying to solve this irritating problem that had been, you see, if twistor theory is meant to be a theory of physics, then you should be able to meet these deformations, not just for, you see, the deformation is defined by a -2 homogeneity function. And a -2 homogeneity function corresponds to a left-handed graviton, if you like. And if you want to do the right-handed graviton, let's see, I'm trying to find the picture I had here. Yes, these were all the, showing you the different homogeneity degrees in relation to the different helicities. So you see -2, I suppose it is. You'll have to tell me which the right one is because I can't see it. Corresponds to the spin -2, or helicity -2, corresponds to homogeneity degree +2. So you have a +2 homogeneity degree, and these +2 homogeneity degree functions tell you how to make these deformations. And how do you do it with the other helicity? Well, you see the other helicity is this crazy -6 in here. And so it's completely lopsided. And this is problem of how you do it with -6 was what we referred to as the Googly Problem. And those of you who know about cricket would know what googly is, I suppose. It's a ball which is bowled, which spins right-handed with an action that makes it look as though it's left-handed. And this was an appropriate terminology. I think Richard Ward may have suggested the idea originally. And that was of the terminology, I should say. But the problem here, this is this big googly problem. And when I say I tried all sorts of things to try and get the -6 functions to give you solutions of the Einstein equations and this and that, and nothing ever worked. And finally I got something which I'm quite proud of. And the trouble with it is it only worked if scry is null. And if scry if you have a positive cosmological constant, then I knew that scry would be space-like, scry being conformal infinity. So I knew it would be space-like, and the whole construction simply didn't work. And I remember that this was a time when people had seen these supernovae things, and they were getting pretty convinced that there was a thing they call dark energy, which would be clearly cosmological constant to somebody who believes in GR to that extent. Cosmological constant. And I remember talking to Jerry Ostreicher and saying to him, well, look, surely these supernovae observations, they could be just dust or something. And he said, no, that's not the point. It really solves a huge lot of other problems in cosmology to have this lambda term. So I thought, oh, well, I suppose I'm going to have to accept it. And it took a little while before I accepted it properly. And I'm grateful for it because the cosmological view I hold now depends upon it being positive. But we'll see actually that it's very crucial to have a positive cosmological constant. And if you have a positive cosmological constant, then oh dear, I probably put it somewhere here. No, not that one. No, I'm afraid I've slipped up here. Anyway, this is the Googly Problem. The Googly Problem is how on earth, in a framework which is geared to the left-handed gravitons, how on earth do you make it work for a right-handed one? And so I had to abandon the idea I had before, that no matter how proud of it I was, because it didn't work when there was a cosmological constant. And it took ages to get hold of another idea, which is what I want to describe to you, and that's the main point of the talk. And I want to make sure, how much time do I have, just to see?
You have another 20 minutes.
20 minutes, okay. This has to be fairly rapid, because I'm afraid that's squeezing a lot of ideas into something fairly rapid. What I was trying to find, and I probably put it down somewhere without thinking, was the infinity twistor when you have a cosmological constant. And if I did show it before, no, here we go, this is it. You see, the infinity twistor used to have a 0 where you see the lambda here. So it's down here and up there, is it? I'm sorry, there's something wrong?
If you could just move the slide up a little bit.
Which way is up? Yes, that's up, is that way, but I wanted to have it down here for the moment. Yes, yes. You see here we have the infinity twistor. Instead of having a 0 where there used to be a 0, which in some respects was nice, to have a thing which was singular, and if you're thinking of exact sequences and things, it's a nice thing to have. It took me a long time to realize it was this, the other was nicer. To have an infinity twistor which is actually non-singular, and then you have a symplectic structure which is a genuine one. I'll come to that shortly. But this is the infinity twistor, and it's non-degenerate, and you stick it onto itself and you get something with the cosmological constant in it. And you have now this two form, if that's a two form, yes, and so on. Now I want to explain, when you have a cosmological constant, this two form that one used to have, which was degenerate, you now have to add this. When I say W, I should explain, because that will be important in a minute. W is really Z bar, but where you're interested in keeping it away from being Z bar. So you want to sort of separate the twistor Z from its complex conjugate and sort of complexify things, and for many things that's very useful to do. So you keep your complex conjugate as a separate independent object, and then when you get to the end and you're talking about real things, the idea is you make W equal to the complex conjugate of Z. So that's, but for a lot of your calculations, keeping things holomorphic, it's very convenient to separate the complex conjugate of Z from itself. In other words, you make its complex conjugate, you generalize so that it's a complex thing, and the Z bar becomes W. Okay, so I'll be using a lot of that in what I want to say in a minute. And I'm going to talk about these forms now, this theta here and this other one. I better keep this aside because that will be important for what I want to do shortly. Now, what's the idea now? Not the ideas that I had for trying to solve the Googly problem. I mean, I'm not going to read all this, but it just explains the problem. How do you try to bring the left and right things together in some way with some description in which you're not stuck by having your helicity given to you, and you've got to deal with -6 functions instead of +2 functions, and how do they lead to sensible perturbations of your standard twistor space. Okay, now let's go back. If I hope I've got these things in the right order. These are the yes, I said I gave you that slide already. Let's put this over here somewhere. I think I gave you that one already. What's the idea? Let's just see, what am I talking about? I gave you this already too. That was the massive particles. What's the general idea? Well, the general idea partly came when I was having discussions with Michael Atiyah, and I got that thing out of order somewhere. How has all that happened? I know, in this place, yeah. Okay. Here we go, this is it. See, the idea is the following. I remember having this conversation with Michael Atiyah at one point. He was always produce the, if I got stuck on something, I'd asked him and he would usually produce an answer, which happened to be the case here. I was getting to realize that you had to do your patching in some way where you didn't actually know what the space was. The problem with the Googlies, as I was realizing, is that if you actually were trying to patch two spaces together, then you've got to know where the points are in the space. And the trouble with the points in the twistor space is that they represent alpha planes. I didn't talk about that here, but they represent when you complexify, they correspond to this particular family of planes in the complexified Minkowski space, which are called alpha planes. And alpha planes correspond to the points when you complexify. And so if you're going to match things with points, then you've got the points. And if you've got the points, you've got the alpha planes, and then everything's anti-self-dual. So the problem is the points in twistor space. So how do you do it without the points? So the idea is that somehow you know the functions, the sheaf of functions or the algebra of functions or something like that, and then you try to patch the algebras rather than the functions. And I was a little puzzled by this, and so I asked Michael, I said, well, how on earth do I do this? I want to try and patch the functions together without the points. And he said, well, that doesn't work, because if you've got the prime ideals here, you know the points, which I sort of knew, but I hadn't quite faced up to. There was just a little pause, and then he said, but that's not true if the algebra is non-commutative. And so I thought, my God, non-commutative. Well, we have a non-commutative algebra going way back. That's the Twistor algebra. I probably can't find my slide after all this, especially since I can't see it. I think this will do. Here we have these commutation relations. They're perfectly natural. They're not even necessarily quantum mechanical. As I pointed out with those quantum integrals, when you go from one velocity to the other, you naturally introduce these, the z bars being d by dz's, roughly speaking, and that's the non-commutative rule. So this is the algebra. It's been sitting there for a long time, and why don't you use it here? So this is the general picture. You have a thing which is not really a space, but it sort of knows its functions, and these functions are functions which have this non-commutative structure to them. And you have this patch of functions, and you patch together the functions, not the space. And that is the general idea. This is what we call Palatial Twistor theory, and this is the basic idea of the whole thing. Now, how on earth do you make it work? Now, it took me years, I would say, after that sort of key idea, which was to use non-commutative things to patch these things together. You use exactly the same ideas as before, but now you're using the algebras rather than the functions, and the algebra has to be non-commutative algebra. Okay, so this is what Palatial Twistor theory is about. And, well, this is just the general idea. But there's a sort of problem which I don't know the answer to. And I've sort of plunged away without worrying about the answer to this problem. Sorry?
You're getting on towards the end now. Right?
Oh gosh, how many seconds have I got? And as you work that out, I'll hurriedly yes.
5 minutes.
Oh gosh, no, I'll have to race through it, but I'm afraid this is the main point of the talk too. Okay, you've got to patch together these non-commutative things. And let me find my right transparencies. Okay, well, one of the key thoughts that I had later was, okay, I don't know much about algebras, but let's think of the algebras as something geometrical. And here the idea of geometric quantization, Nick Woodhouse was a big influence in this. And for a geometric quantization, what you need is a symplectic space, and you construct a circle bundle over this, and then you look for connections in the circle bundle, and you get non-commutative algebras. So the idea here is, what is the circle bundle? Well, you see, if you think of your space here now as the space of light rays, but you want to make it into a symplectic space, so what you have to do is to scale the light rays so they've got a momentum scaling to it, and I'm not sure I can see what I'm doing here. But I shall have to rattle through this, I'm afraid, even though that's the main idea. The thing is that the space Pn, that is the projective, I'm talking about a space now which is curved, and I suppose it's globally hyperbolic to make things work nicely. The problem I was mentioning you do have is how do you know what a neighborhood means and all that? The trouble is when you go to the function e to the z is very beautiful as a function. When it's an operator, if you make z into z bar, then z bar becomes d by dz. And what do you mean by local here? Because the trouble is that this operator shoots you outside your patch. And so you might have a singularity outside the patch, and it notices that singularity. And I don't know how to make sense of that. I'm sure there is a way of doing it, but that's for the future. The null rays have a symplectic structure if you scale them. So I'm going to call the space little p n, and I can't see it here, never mind. The scaled light rays, the space of scaled light rays, when I say scaled, they've got a momentum scaling. And this is now either written in terms of standard flat space twistors. Oh, well, I'm not sure it's the right slide, never mind. You better move on to the next one. I think it may help. See, the momentum is null, and so it's product of pi's, but it has a scaling, because the momentum it's not just a direction, it has a scaling. And the space has a symplectic structure, which is what I call little p of n, and I can't see it on the slide, but little p of n is the space of scaled light rays. And so that's symplectic manifold. And I want to apply the procedure of geometric quantization to that symplectic manifold. And the procedure of geometric quantization, you construct a circle bundle over that symplectic manifold. And the thing is that in twistor theory, the circle bundle is already there. So you think of the null vector or null covector, and it's got a little flag plane attached to it because it's naturally in twistor theory or in spinors for that dimension, the circle bundle actually corresponds to the flag plane. So the space, which I referred to as n, has that scale as well. And so that space n, curly n, is a circle bundle over a symplectic space. And so therefore you can apply the procedures of geometric quantization, or pre-quantization, really. You don't go as far as what's called geometric quantization. It doesn't matter too much. You're looking for connections in the bundle, which is the circle bundle over the symplectic space. You've got this connection. You see, the idea of geometric, well, pre-quantization is you construct a connection. And this connection has a curvature. And you have, therefore, so you're looking, see, what I want to do is represent the non-commuting twistor algebra in terms of a bundle connection. And that's the idea. The bundle is the circle bundle over the symplectic space, which is the space of scaled light rays. Now, how do you write down a connection? Well, this is the connection. You've got a piece here. You've got d by dz and d by dw. I've complexified it. Locally, you can always complexify these things, and so I imagine I have a local patch where I can pretend it's flat space by introducing the z's and the z bars in the standard way. And there's no obstruction to doing that. It's just not canonical. There are many ways of doing it. It's not canonical. But nevertheless, you can certainly do it. And so here we have the connection. And the P and the Q are related. Well, you see, to get this thing, you start with the scalar product, z dot w, and you split that into E plus F. And there are lots of ways of doing this splitting. And for each one, you have one of these connections. So what you do is you construct the P and the Q, and then you construct phi, which is the connection. And this is non-commuting, and you get the commutators, which are the standard twistor commutators from this construction here. I just have to tell you here because it's a bit difficult to explain it. Now you see there are two canonical ways of doing this. One is to split it simply into that F is the whole thing. And when you do that, then you get let me put it like this. You see, you have an algebra. You have your splitting your two pieces into two algebras, and the algebras have to match on the overlap. But on each side, the algebra is represented as linear operators on a Ket space. So you're thinking about quantum mechanics. So your things are represented on a Ket space. Now the idea is that you don't have a consistent Ket space over the whole thing. You have it locally here, you have it locally there, and the fact that you don't have a global Ket space is where you get your curvature from. So this is the key idea. You have the operators. Do you represent the operators as algebras on a specific Ket space? Sure, you can do it locally, but the point is you can't do it globally. And that's the key point to what you do here. See, what you want to do is to represent, you see, you have a patching, and this patching is to preserve the symplectic structure as you go from one side to the other. And the way you can do that is use a generating function. So you have a generating function, which is this thing g here, and it's a function of your, So I've got the curly Z and W over on one side and the straight Z and W on the other side, and I want to patch this together in such a way that the symplectic structure agrees on the two sides. And so I do that with a generating function where you have half the variables from one side, that's the Z's, and the curly W's on the other side. So that's your generating function. Then you construct your map from one side to the other in the standard way with generating functions with the Legendre procedure. So your curly Z's then become d by d curly Z of the generating function, and your uncurly W's become d by d uncurly Z's of the generating function. And this gives you the symplectic functions agree. And so this thing gives you the algebras then you can match from what I did before on the previous slide using the geometric quantization. And it's very explicit, and it is geometrical. I sort of worried about this because it's all algebraic, and what do I know about algebras? But at least you can represent this as this geometric, these connections. Now, this is giving you a general Lorentzian manifold. Well, for the moment, it's not Lorentzian. I've just got complex structure. Complex Lorentzian, if you like, which doesn't mean much. But you're producing the general space. So it gives you, if you like, a conformal manifold, which is curved. And the fact that you can do this depends on this sort of quantum procedures. So what's kind of ironic about this, you're using these non-commutative properties, which come from quantum mechanics, but I'm just building a classical curved conformal space. And this does it. OK, but it doesn't give you the Einstein equations. This is just general. It doesn't even give you a metric. OK, next slide. And this, I think, is more or less preferably, can we move it up a bit? Yes. For this, you need the infinity twistor, which I've now written with the cosmological constant. I tried endlessly to do it without outer cosmological constant. It simply doesn't work. You also have to, OK. Now, in order to try and get the Einstein equations, you need to preserve this form. Now, this form gives you the infinity twistor, but along with giving you the infinity twistor, it gives you the Einstein equations. I won't go into the details of that, but the whole point is, as soon as you've got your actual metric, not a conformal metric now, but an actual metric, which means preserve this I alpha beta thing, you also get the Einstein equations. And when I say Einstein equations, it's vacuum equations with cosmological constant. Now, how on earth do you preserve that form together with the one we had just had? So we had to preserve the symplectic form thing, and now we've got to preserve this as well at the same time. And how do you preserve both with the same generating function? Well, here's where a completely crazy trick comes in. What you do is you choose this completely daft collection of components, some from the Z's, some from the W's, some from one coordinate system, some from the other. And it has to be something like this completely crazy combination of Z's and W's. What's lambda cross? That's I times the square root of cosmological constant over 6. And when you write these completely crazy collection of coordinates, then what you find is if you make it symmetric in two ways, one is, I've got it written here, if you interchange the first and the third and the second and the fourth, or whatever it is, then it's invariant onto that. And if it wasn't originally, you can easily make it do by adding this to the flipped over one, and then it's got that symmetry. What about making it real Lorentzian? You can do that with a different symmetry. It's that when you reverse the order of these things, it's written down here, and I hope you can see it. That's another symmetry, which is now a Hermitian type symmetry. And you can impose that also generically as well, because it just means adding this to the Hermitian conjugate. So then you have this function, which has those symmetries, and this symmetry changes one form into the other. So if it preserves one, it does automatically, because that's the normal Legendre trick. Then because it's got the symmetry, it preserves the other one. So you preserve the form, which gives you the Einstein equations. And so the idea is this does give you a generic construction for the general vacuum lambda solution of the Einstein equations. Now, of course, there's a whole lot of stuff here. One is, does it really? Second is, does it? These functions have got to have the right structure so that you don't have a global ket space for the whole thing. So you've got to be careful to make sure it does what you want. how do you recognize the points in the space-time? Well, the points are, you can see that if you had the points, they would give you subalgebras. Each point gives you a subalgebra of the complete algebra, which is 4-dimensional, completely commuting, and self-conjugate. And you can see that's true because it's really what the pi's, you have the pi's at that point, and the pi's go into themselves onto conjugation, and they commute with each other, and they commute with the pi bars, so you have an algebra of that nature. I asked Keith Hannibus, who's my roommate in Oxford, and I asked him, what happens if you look at Minkowski space? Are these completely commuting 4-dimensional Hermitian self-conjugate algebras, do they give you the points in Minkowski space? So he went away and came back with a proof stack of papers like this, and he said, what you said is essentially correct. I slightly worried about the essentially, but what that means is you get points at infinity as well, which I knew, forgot to mention it to him. So it works for Minkowski space. Now, in the general case, you will get these completely commuting subalgebras, which are self-conjugate. The question is whether you lose them. Well, you're not likely to lose them because you have them in general. You certainly have these algebras. Do you gain any? Well, you're not likely to gain any when you perturb the space. So it seems to me it's likely that this is correct. That is to say, you do find the points if you can find those subalgebras, and that therefore you would have, according to this proposal, a completely general solution of the Einstein lambda vacuum equations. It's probably a huge operation to try and do it explicitly, but at least it's a way of representing these solutions as far as I can see. It needs some work. It needs probably a team of graduate students or something. I've not worked any of these out explicitly. It would be very intriguing to see, look for the Schwarzschild solution or something like that, guess what the generating function is for that, and see whether you get the right answer. Thank you very much. I'm sorry it could rush at the end.
Well, you'll appreciate we're behind schedule, but I'm sure there are questions, and I believe we're going to eat into our coffee break and have a few minutes now for questions. Is that right?
Well, maybe a couple of questions.
And then we'll have a short...
Okay. Yeah.
Okay, right. So, questions?
Well, there are no questions. That's easy.
well, I mean, you need a sort of Kadara-type theorem to make sure that...
Yes. No, you certainly do need a Kadara-type theorem, yes. I don't know what that is.
Right, and so there isn't one on the shelf that you're aware of?
No. It just seems to me unlikely that that fails, because as from the Hannibus theorem, you'd have to... You see, in this case, you know that in general you do have these completely commuting algebras because they come from the points. Right. So if you've got the points, then those algebras are there. It's just whether they characterize the points. So...
George has a question?
Yeah. Well, okay, so this is physics.
That's the intention, yes.
You're saying lambda is not zero.
Positive.
There is one question. Suppose it turns out that it really is zero. But apart from that, let's assume it's non-zero.
Yeah.
The question is the scale of it. We've got Planck's constant in the theory.
No.
About the scale of lambda, is it 10 to the minus 121 or whatever it's supposed to be? Or is it 1? And the other thing is in your lambda formula there, you've got an I on the outside. It might be more natural to put it on the inside, in which case you've basically got minus lambda instead of lambda. So
it has to be positive. It doesn't work. Yes, there was another slide which I should have shown you, oh dear. Yes. There was another slide. Yes, what your question reminds me, you see, from what I say, there's actually isn't any another number involved in the theory. The lambda doesn't tie in with the... You see, here's where you would see it. If you change the other form into a commutator, which is I've not done here, but if you change the other form into a commutator, which I think I've written down here, then there is a number here, which I've called zeta. And that number it's something to do with the ratio between the Planck's constant and the cosmological constant. So you see you have a Planck length, which is 10 to the minus 33, whatever it is, centimeters. and you have the cosmological constant, which is reciprocal of something which is much, much bigger, and you've got a number which is of the order of 10 to the 60 or 10 to the 120 if you square it, which relates one to the other. And so those numbers would be in here. You just put them in. But that only comes in when you put the commutator here for the... I don't think you see it until you put that commutator in. But you're right. You do, if you really go the whole hog, and you put the second commutator in, which is now some form of quantum gravity, presumably. All I've been doing would be classical Einstein theory. If you want to do something like quantum gravity, you would make this other form into a commutator as well. And then you do have a number, which is some vast number of the order of 10 to the 60 or something like that. So yes, that's true. But it's fed into the theory. It doesn't come out of the theory.
So at the moment, all the numbers are of the order of the Planck.
Yeah, all the order, yes. I don't think, I have to think it through quite well. You don't see it at this point. But the lambda, I don't think you fixed the scale on that. It's just, that's freeze. But you've set me worrying because I can't quite see why this doesn't have a value somewhere there. I don't think it comes in at this point. It certainly comes in when you put the commutator in for the other, the theta form, yes.